So if you're taking the derivative, then you're taking the derivative of the function over the function. So if we're doing derivative of natural log, this is what we're doing, right? So now we're going to do antiderivative of the 1 over x, an antiderivative of the function that maybe necessarily is not x. You'll notice they have absolute value there. Because if you'll recall from the last section, when you had absolute value, then it converted to the same thing. It didn't matter if it was positive or negative, right? And so this is also true, and this is why we do absolute value, so there is no negative when you go back into it. And so you're going to pop in that absolute value. Sometimes you'll see that they take the absolute value out, but it's because it's no longer valid. And that, in fact, the first example, they took the absolute value out because it ended up being a square. And so when you're going the other direction, if you have 1 over an x, then you're going to take the antiderivative back to natural log, all right? So let's look at these examples. Use the log rule for integration. All right, remember that 2 is just a constant in front, so we can pull that 2 out, and it's just 1 over x, which means we can have 2, and this antiderivative is the natural log of the absolute value of x. And then our condensing rules, right? If I have a 2 in front, what can I do with it? Well, that can become my exponent. So natural log of x squared. You'll notice I no longer have the absolute value. Why not? Well, x squared is always positive. I don't need an absolute value there. For something like this, you're going to want to think of it like u substitution. And you can write it out like u substitution if you need to. My more difficult guy on bottom is going to be my u. My derivative here would be 4 dx. You'll notice there is no 4. All right, so you do have to account for the derivative of this just like we did before. So I would need to multiply both sides by 1/4 because there is no 4 in my original function. And so if I were to rewrite that, I would say, okay, it's 1/4 integrating 1 over u du. And you can see that that's just natural log. Instead of u, I'm going to fill in what u is. You could do the 4th root here if you wanted to. I don't know that it's any simpler to do 4th root because 1/4 is technically a root. But if it were square root, if it were 1/2, you potentially would want to do square root there. But it just depends on whether it's more simple to leave it one way or the other. Find the area of the region bounded by the graph. There's another way to say that. Find the antiderivative, okay? In this case, they actually give us boundaries, x-axis and x equals 3. That is actually 0 to 3. So we're going to go from 0, that's where my x-axis starts. 3 is where they want us to end for this particular one because we're not going before the 0 here. Of x over x squared plus 1 dx. So anytime you see area of the region, your brain should automatically go to that. Area of the region, bounded by, that's the function that you're taking. And if they give you other boundaries lines, which for area of the region you're going to have, those are your boundaries, lower and upper sums there. And so now, again, if I did u substitution, I'm going to do my denominator there. My derivative then would be 2x dx. What's the problem? I don't have a 2. So 1/2 du x dx. I do have the x dx, so that's what I need. And so I'm going to rewrite that using these substitutions here. So 1/2, I can just put that in front from 0 to 3. And again, if you want to replace your 0 to 3, you can, right? So you can plug it in here and change your boundaries if you want to. It's up to you, or you can leave it. This is now just going to be 1 over u du, right? And then you can see that you would have 1/2 natural log of, and we're going to say x squared plus 1, my u. Why don't I need absolute value there? Well, x squared is always positive, right? Plus 1 to any positive number is going to be positive. So you don't even really need your absolute values there. We're going from 0 to 3.
And then we don't add plus c because
We don't need a plus c because we actually have boundaries right here. It is bounded. So I can say 1/2 natural log of, plug in my 3. That's 10 minus my natural log of 1. Remember, natural log of 1, log of any base of 1 is always 0. So that's just going to be 1/2 ln of 10. If you plug that in and round it, you should get approximately that guy right there. So really, when you're doing these and you see something in the denominator like this that is to the first power, like if this denominator was squared or something, I would not need a natural log here. I would do u substitution and just do my exponent rule, right? But to the first power, my exponent rule gives me a 0 in the denominator. So anytime my denominator is to the first power, like all of these are, you're going to look for probably a natural log. I mean, that's likely what's going on if you can't divide it out, okay? So then the next thing I'm going to look for is my derivative naturally already in this function? What's the derivative of x squared plus x? Oh, it's 3x plus 1. It's completely taken care of. I can go straight to my natural log of x cubed plus x plus c because it's all taken care of right there. All right. What's my derivative of tangent? Well, it's secant squared. So I can go straight to natural log of tangent. All right. If it's not automatically there, let's say this guy. The derivative of that is 2x plus 2. Well, there's another way to write that. 2 times x plus 1. So what am I going to have to multiply by to get rid of that 2? A 1/2, right? You're going to divide by that 2. So you can go straight to 1/2 natural log of x squared plus 2x. If you know what you have to pull out of it. Just like this last one, my derivative of this guy is 3. I don't have a 3 to deal with, so it would be a 1/3. 1/3 natural log of 3x plus 2 plus c. All right? So you can jump right to it if you can see what the substitution would yield. And you don't have to set up the whole u substitution if you can see immediately what you would divide or multiply by. When you see something like this, if you do use substitution, you're going to have an issue because it's not going to derive out of it. You're going to the derivative of that denominator is 2x. And obviously, we have an issue with 2x because on the top, we also have an x squared. So if you have a polynomial on top of a polynomial, you have quotient going on, and you have the same degree, or the numerator is higher, you're going to have to do something to get rid of that. And really what you need to do is divide. So if it just had a monomial on the bottom, you could put each piece over the monomial, right? But we have a polynomial on the bottom. We have a binomial down there. And so you want to do long division, just like we did in pre-cal. And so when we do long division, it's just like we would have done prior. We're going to do our long division like this. Right, we're going to say x squared times what to get to my x squared? That's going to be a 1, and then multiply it through. If you do not have something that lines up, just 0 it out. All right, and remember we're subtracting, so we're adding the opposite. These will cancel, these will cancel. You're left with an x. And so this is technically my remainder because my degree is lower than what I'm dividing by. And so my answer is going to be, if I were to, now that I've divided it, I would actually get 1 plus x over x squared plus 1. All right, because this is my remainder right here. So my remainder goes up here with my denominator in the bottom. And so I actually did this division. So it's like if this were like 6 over 3, you would say, oh, well, it's just 2. It's the same thing because I did the division. So when you do the division, this is your answer. And so now we can integrate our answer. And we can integrate them individually, right? If you have an integration of a group, you can take each piece individually. And so the antiderivative of 1 is just x, right? The antiderivative of this, well, I have a denominator to the first power, right? What's my derivative of my denominator? It's 2x. What do I have on top there? Just an x. So I'm going to have to say, oh, well, that's a 1/2. And because it's a denominator to the first degree, that's going to be a natural log function. And you don't really need an absolute value there because it is going to always be positive. You do need your plus c. So when you first see this, when you're not going to think natural log, because your denominator is to the second power. So my first thought is not natural log here. My first thought is u substitution, however, okay? Because my numerator is not the derivative of my denominator. So I can't just go straight to like exponent rule, okay? If that numerator were a 1, then I can just rewrite this to a -2 power, add 1, divide by my new power, etc., and I'd be done, okay? But that's not the case here. So I am going to have to do u substitution, the old-fashioned, like how we did it when we first did u substitution. All right? So I'm going to take the x plus 1, and I am going to make that my u. I'm going to do my du. Well, my du is going to take care of my dx. All right? So if we look at my u substitution piece, I've taken care of this, and I have taken care of this. All right? So what piece I am missing is the x. The 2 can go out in front, right? He's just a coefficient. So the 2 can go out in front of my antiderivative, all right, my integration. But the x is an issue. And so I need to rewrite x in terms of u. So if I were to say u minus 1, that would equal x from my original setup, okay? Everybody agree with that? So now I'm going to rewrite my antiderivative here with my substitution pieces, okay? So I am going to say antiderivative, I'm going to pull this 2 out in front, all right? I'm going to pull the 2 out in front. My x I said was u minus 1, right? And my denominator, that x plus 1 is u. So I'm going to say over u squared. So far, so good. All right, du. Now this is just like the first one from homework. I have some polynomial over a monomial, over a single term. I'm going to split up my numerator into pieces over my denominator. All right, so I'm going to leave that 2 there. And I'm going to say that, well, this is u over u squared minus 1 over u squared du. So far, so good? Can I reduce? Well, yeah, that first guy can reduce. That first guy reduces to 1 over u. The second guy doesn't reduce, but I could rewrite him to make him easier to take the antiderivative. Just make him u to the negative 2. Yep. Over, and then du, of course. So at this point, I have simplified this as much as I can. I need to actually take the antiderivative. And now I should think natural log because I have 1 over u to the first power. Automatically, that is natural log. And so I am going to do this piece by piece. I'm going to say 2 is out in front. This piece of it is going to go, integrate to natural log of u minus this piece. Well, this is just an exponent. So I'm going to say add 1 to my exponent. What is negative 2 plus 1? Negative 1 over my new exponent of negative 1. All right, and then I'm going to simplify this a little bit more, all right? I'm just going to distribute that through, and I'm going to simplify this guy right here, okay? So distribute the 2 through. I have 2 natural log of u, right? This becomes like minus a negative, right? You see this guy and this guy here? So it's going to be plus, and I'm going to rewrite him to be 1 over u. But because I distributed that 2, we're going to actually say 2 over u, okay? Because I distributed that 2 through. So all I did was simplify those. And now my last step is to plug my u back in, right? I can't leave it in terms of u. I need to actually go back up here and plug him in. So the final answer here is going to be 2 natural log of the x plus 1 plus 2 over x plus 1 plus c. That is my antiderivative there. Guidelines for integration, you may want to look at them in your book. Learn the basic list of integration formulas, all right? You have the power rule. You now have the log rule. You have 10 of your trig rules. And by the end of this, you'll actually have more than 10. Find an integration formula that represents all or part of the integrand, and by trial and error, find a choice of u that might make it easier to use, basically, okay? So your first thought, you need to make sure your first thought is the path of least resistance. By that, I mean, in your homework, when you had 1 over square root of something, you automatically went to like natural log brain. That's not the path of least resistance. In fact, that's not actually going to help you at all. So you need to the very first thing you need to do is look at what you are integrating and saying, is there a way to simplify it? Is there a way to reduce it? Is there a way to rewrite it? Okay. And then once you've done that, then you want to say, okay, do I have something to the negative 1 power or to the 1 power in the denominator? That's natural log. Do I have something that just requires basic u substitution? Okay, do that. Or is there something that just requires a basic power rule? Do that, right? So you're going to want to go through this path of least resistance and work your way up to, do I need to take the natural log of both sides and separate it out? Would that be easier, okay? What do I need to do to make this process easier, okay? If you can't do u substitution, try altering it. Try trigonometric identities, which we're going to look at some of those. Some things you may have to do to manipulate it to be able to find your antiderivative. All right, so half the battle is recognizing what you have, all right? So, for example, if I were to look at this one, this said solve the differential. This is the derivative, so they want you to take the antiderivative. So really what they're asking you to do here is to do the antiderivative of this guy, okay? This is just another method of manipulating fractions. So I can look at this another way. I could say, well, that's the same thing as 1 over x times 1 over ln of x, all right? How does that help me? Well, let's talk about u substitution. My most difficult of my equations here is my natural log of x, right? When I look at this. So if I make my u my natural log of x, what is my du? What's the derivative of natural log? 1 over x dx. Do I have 1 over x?
Yes.
Yeah, I do. So I could actually rewrite this to just be 1 over u du. Yes?
Yes.
Because my u is taking care, my 1 over x takes care of the derivative of my natural log of x. What is the antiderivative of 1 over u?
Natural log.
The natural log of u plus c. And then my last step is to plug in my u. And yes, you can have natural log of the natural log. Okay? All right. Antiderivative of tangent. We know derivative of tangent, but we have not talked about the antiderivative of the tangent. Okay? So here you're going to have to go back to just basic trig properties. What's another way to say tangent? Basic way. Yes. And so I could rewrite this sine of x over the cosine of x. All right? Let's do u substitution. If I said that u is my cosine of x, what is my du? What's the derivative of cosine? Negative sine of x dx. Do I have negative sine? Well, I have positive sine. So I can just pull that negative out. Put a negative here. 1 over u du. What's the antiderivative of 1 over u? Natural log. Don't forget your negative there. Natural log of u plus c. What was my u? Well, that was cosine. So the antiderivative of tangent is the negative natural log of cosine. That is your antiderivative of tangent. So this is just the proof of why we're about to do these trig functions, all right? With secant, you do not naturally have something that you can do because secant is just 1 over cosine. And so the reason you can't just do, oh, well, natural log of cosine is because cosine has a derivative of sine that is missing in your secant, all right? We just proved natural log of cosine plus c is tangent, right? So that's what we just proved there. So with secant, the way they do this one is they actually multiply the top and bottom by secant x plus tangent of x. You would never, ever, ever think to do this. Okay? This is not by intuitive, you wouldn't think to do it. All right. Intuitive means that it naturally would be something you would think about doing. It's not. Okay. So you do end up with like secant squared plus tangent secant over secant plus tangent. So you distribute that guy, you get this right here, secant squared x plus the tangent of x over tangent, secant, tangent, whatever, over secant of x plus tangent of x. And then what happens is now you have u substitution, because if I were to take the derivative of this guy, okay, the derivative of tangent is secant squared, the derivative of secant tangent. So you end up with this guy right here in your natural log. So if I were to do this, it would end up with the natural log of secant plus tangent, which is your antiderivative of secant. You do not have to remember how to get that, okay? I'm just showing you how they go through this process. They go through the process of all of these ones we haven't learned yet by this type of process right here. And so that is where we get this chart, okay? That is where we get this chart. Some of them we already know. Some of them we did not already know. The antiderivative sign is negative cosine. We know that one. The antiderivative of cosine is positive sine, because remember it's opposite. These four we did not know, but one of them we've already done. And then I just did this one for you. So now the easiest thing for you to do is to memorize these last four, okay? So we automatically knew sine and cosine. Antiderivative sine is negative cosine. Antiderivative cosine is positive sine. For tangent, it's natural log of the cosine. For cotangent, it's natural log of the sine. Tangent does negate though. So antiderivative of tangent is negative natural log of cosine. Antiderivative of cotangent is natural log of sine. Okay? Secant is natural log of secant tangent plus tangent. Cosecant is negative natural log of cosecant plus cotangent. So they do pair up nicely, but it is much easier to memorize them. The only one you're probably going to be able to do without memorization are those tangent and cotangents, because you could rewrite those and do natural logs, right? But the secant and cosecant are not intuitive. So those two you definitely want to remember. Tangent and cotangent you can rewrite as a fraction and probably glean the natural log from there. But the other two are not as intuitive. So here's the thing. Pythagorean identities will forever haunt you, okay? So if I look at this guy right here, I should recognize that 1 plus tangent squared is secant squared. I'm sorry, you should know that. I can rewrite that as the square root of secant squared. Well, what's the square root of a square? They just cancel each other out. So this is like doing the integration of secant of x. We just did antiderivative secant, right? It is the natural log of secant of x plus tangent of x. You notice that I have an upper and lower bound. It's like anything else. Just plug it in. Plug in pi over 4. Subtract what happens when you plug in a 0. And you would use a calculator to do this because you're going to get a decimal, okay? So plug in pi over 4, plug in 0, subtract it as your answer. All right? So you do, when you're looking at trig functions, part of simplifying is, are there any trig identities like rewriting tangent to sine over cosine? Rewriting 1 plus tangent squared to secant squared. Some of those basic trig identities, not the really difficult ones, but some of the basic ones, especially when you're doing integration, you want to try to remember, because there could be a simpler way to do it than trying to do like a u substitution here.